Hey physics students, we're going to start off our fluids discussion by talking about static fluids. In particular, we're going to talk about what is a fluid, what is density, what is pressure, and how do I use them in physics. Well, first of all, what is a fluid? Well, a fluid is a substance that flows. Now, we all know that liquids are fluids. We see that in commercials where they talk about replenishing your fluids. But gases are also fluids as well. Gases, though, and liquids are a little different in their behavior as fluids, but they're fluids because they both flow. Gases, if you remember back to chemistry, there's a lot of space between the molecules. They're in constant motion. And one of the properties of gases is that they're compressible. This is different from liquids. Liquids, right, the molecules are more packed together. They're still able to flow, but they're not as compressible. And how can I show you that? Well, I have a bottle here which I have filled with air, and I have another bottle here which is actually filled with water. Now, if I squeeze them, right, you can see that the one filled with air is much more compressible than the one filled with our water. But they're both fluids, and that means they both behave a little differently, but we're going to assume, to make things more simple for us, that our fluids are all incompressible. Not really true, but we'll pretend. Another property we need to know about is density. Now, we're talking about mass density in this unit. There are different types of density, but for this unit, since we're just talking about mass density, we're going to just call it density. Now, mass density, the symbol for density actually is a rho, the Greek letter rho. It's the amount of mass divided by the volume. The SI unit for density is actually kilogram per meters cubed. However, in chem, a lot of times we use grams per centimeter cubed. So if you ever run across grams per centimeter cubed, you need to convert it into kilograms per meter cubed. Fluids all have different densities. Gas, obviously, because the molecules are farther apart, have much lower densities than our liquids. Temperature also affects density, but density is a useful property. One, I can use density if I have something I don't know and I want to know what it is. So, for example, I found this in the closet and it looks like gold. How do I know it's gold? Well, I could get the density of it, right? I have scales in my classroom and I can measure the mass of it. I have a caliper here and I can get the dimensions and I can use the equation for a cylinder, since it's kind of like a cylinder, and I can calculate that. And if I do that, to calculate the density, I found that the density of this material is 8,683 kilogram per meter cubed. So then I went and looked up gold, right? Gold, the property of gold is, you can't see that, can you? Oh, I'm really not good with backwards. So I looked up the density of gold, and it turns out that the density of gold is much higher than that. It's 19,320 kilogram per meter cubed, so unfortunately not gold. Turns out that what I had is actually brass. Back in the closet for you. But what else can we do with density? And how does this apply to fluids? Well, what if I want to know the weight of air in this room, right? In physics, we always need to know how much stuff weighs, right? Weight, mass times gravity, right? That's the force of gravity. And that's important, right? Because when I build a structure, I need to know how much weight is going to be resting on the beams in the floor, right? Make sure the floor doesn't collapse. Well, how do I get the weight of air in this room? I mean, I can't exactly stick it on a scale and measure it. But I can use density, right? Because I know what the density of air is at specific temperatures, so I picked 20, right? That's 1.2 kilogram per meter cubed. And then I can figure out the mass by using that density and the volume of the room. So I measured the volume of the room, and of course, this isn't exactly my room, but it's, fairly close. And I can get the volume of it, right? Length times width times height will give me the volume of this cube here. I multiply that by the density, and then that'll give me the mass, right? And then times 9.8, the acceleration due to gravity. And I can get the weight of air in this room, which turns out to be 1,764 newtons. Or if I wanted that in kilograms, right, we just get rid of that 9.8. And it turns out to be 180 kilograms. Not bad. Now I know how much weight there is in this room from air. See, air does actually have mass. Now, I question for you. Since we're talking about fluids, I have a container here, and it has holes in it and a liquid. And I'm going to take the tape off these holes. What's going to happen? Is the liquid going to stay inside this container? Probably not, right? Now, besides what's going to happen, I want to know which, if it comes out, where is it going to come out the fastest? So where is the highest velocity going to be? Well, let's find out. Let's take some tape off here. Oh, let me take the top off. Huh. That would be helpful. All right. Now, how do I know? Well, I can tell speed by how far it goes, right? Something that's traveling at a faster speed goes farther. So obviously the one on the bottom is traveling the farthest. And as the water level goes down, now it's not even over this hole anymore. Why does this happen? Why does the fluid come out of the holes? And why is the hole at the bottom, why is the fluid coming out with the greatest amount of speed? So why does the fluid come out of the container? Well, it comes out of the container because there's pressure. Right? The fluid in the container exerting pressure against the walls of the container, and so as soon as we open a crack, that fluid is allowed to escape. So what pressure is from a calculation or a mathematical standpoint, pressure is the ratio of the force applied, in this case by the fluid, over the area of which it's applied. So pressure is force over area. The SI units of pressure are the Pascal. A Pascal is a Newton over meter squared, which makes sense because force is newtons and area is meters squared. Now, a couple things you should know about fluid pressure. First of all, the pressure is, or the force, is always exerted perpendicular to the walls of the container. And you can see that if you think about how the fluid was flowing out of that container, right? It was coming out perpendicular, but then all of a sudden gravity takes over, right? So then it follows a parabolic path, but just like it's a projectile, like we kicked a ball off a cliff. Another thing about fluid pressure is that it's exerting pressure in all directions. So it's not just pushing out, but it's pushing in all directions. Let's take a little further look at pressure in containers, because we know that at the bottom of the container the liquid was coming out faster, which means there must be higher pressure there. So where is this pressure coming from? What is it due to? Well, it's due to the weight of the liquid, right? So that makes more sense that the farther down you are, the more weight, right? The more fluid you have pushing down on you, so that the pressure would be greater. Now, if we take a look at this little diagram here, here's a beaker containing maybe some water, and we look at all of the forces. These red arrows are forces on the fluid, a little cross-section of fluid. Right, we have these forces that are coming in perpendicular horizontally, but they're equal but opposite, so they keep canceling each other out. But if our fluid's at rest, that must mean that the total upward forces have to balance the total downward forces. But you can't tell me that the force due to the pressure above from the atmosphere is the same as the force from the pressure or from the fluid down below, down here. So there must be another force at work. Well, of course, that's the weight, right? If the fluid's at rest, then these vertical forces have to balance, which means my upward force here, which is coming from the bottom fluid here, bottom of the fluid, and my downward force, which is coming from the force above the container and the weight of the fluid, these guys have to be equal to each other. But let's take a look at that, what that means in terms of pressure, right? Because we really want to know what is the pressure down here at the bottom of the container. Well, from an equation standpoint, right, we just define pressure as force over area, so we can rearrange that to have force is equal to pressure times area. So if I take this equation and I substitute it in for my forces, right, I have my pressure at the bottom times the area is equal to that pressure outside from the outside fluid, which in my case was the atmosphere with the air, right, times the area. And then what do we do with this mg term, with the weight of the liquid? Well, if I know how much liquid is in there, right, I could put that in there. But we have density now, right? And if we rearrange our density equation, right, we have that mass is equal to density times volume. And of course, I don't have any volumes in my equation over here, so let's get rid of volume and put in area times height, right? That's equivalent to volume. So that means my mass becomes density times area times height. So I plug that in for my weight, and now we can do some simplification, right? They all have area in the term, so we'll divide everything by area and get rid of that, and we'll get rid of the height, and we'll put in D. So we think of it more as depth in the fluid instead of really a height of the fluid. That ends up with this equation, which is an equation from your book, that the pressure of a liquid at some depth is equal to the pressure coming from above the liquid, which in my case was the pressure to the atmosphere, plus the density of the liquid times gravity, the acceleration due to gravity, 9.8, times the depth inside the liquid. So the pressure at any point in a fluid is directly proportional to the density of that fluid and the depth of the fluid, or how high that fluid is in that container.
Stop! This is the equation for hydrostatic pressure because the fluid's at rest. Once fluids start moving, don't use this equation.
Now, a couple significance to this whole idea is that if pressure is due to the density and the depth, if I put liquid in a container that has these weird openings, the liquid will all come to the same height. So we say that water seeks its own level. So this is because the fluid pressure has to equalize. So when I pour the fluid into this container, the pressure all up here has to be the same. It has to be atmospheric pressure. And that means if I look at any other point here in my fluid, at anywhere along this dotted line inside the fluid, the pressure is going to be the same. So then let me ask you this. If I have this container down here and I fill it up with the same liquid and I get two different heights, is that possible? Well, hopefully you said no, right? Because I just told you that the pressure here has to be the same. Water seeks its own level, or any fluid will seek its own level as long as the density is uniform throughout. So this is not possible. These are different heights, which means their pressures would have to be different, and they're not. So at any depth, D or height, H, below the surface of water, the pressure is the same. So it doesn't matter the shape or the area, as long as the fluid has a consistent density, which is why it has to be incompressible, the pressure is going to be the same. Now let's talk about atmospheric pressure, because that's what was above my container. We said that gas is compressible, right? I squeeze the bottle, and that's true with the atmosphere, right? If we look at the Earth and we look at the air density, right, there's going to be more pressure due to the air at the surface of the Earth than farther out in outer space. Now, that means that atmospheric pressure is different depending upon where you are in regard to sea level. Another problem is weather patterns, right? You've seen a weather map like this here, and atmospheric pressure varies with weather, right? We have low pressure systems, we have high pressure systems. So what do we do if we need to calculate a pressure, if atmospheric pressure could be anything? Well, we are going to pretend that atmospheric pressure is constant. And so we're going to use a constant value. And the way this constant value was arrived at, it's the value at sea level, is by using actually what's called a barometer. A barometer measures pressure. And what, in fact, with a barometer, you fill up a tube of liquid and you seal it with your finger. And then you invert it in a tub of similar liquid without letting any air in. That's critical because you need to get a vacuum above, right? If here a vacuum means there's no air, right? So that means there's no fluid, which means there's no pressure. Now, typically in the old days, this was done with mercury, so you don't want to do that with your finger. But if you think about what's going on, right, we said that at the same height, the pressure was the same. So if we take a look at our little device here, now we have at point 1, the pressure due to the atmosphere pushing down. And here, point 2, we have pressure that's due to the weight of the fluid. But because these are at the same height, that means the pressure here, P1, has to equal here, P2, which means that the pressure of the atmosphere has to equal the pressure due to the weight of this fluid. Now, how they came up with atmospheric pressure is they did this with mercury, and the density of mercury is 13,600 kilogram per meter cubed, and when they did this at sea level, what they found is that the height of the mercury in the tube was 760 millimeters of mercury, or 0.76 meters. So if you've ever heard the term 760 millimeters of mercury, it came from the barometer measuring atmospheric pressure at sea level. So if we plug that into our equation, we get that the pressure due to the atmosphere that we will use as a constant is 101,300 pascals. Or we can just do 1 times 10 to the 5th pascals. This is also called 1 atmosphere, or 760 millimeters of mercury, or 760 torr. There's a bunch of different units, but remember the pascal is the SI unit, and that's what we're going to use in physics. So what we've talked about so far, this pressure due to the density and the height of the fluid and the pressure above, is actually called absolute pressure. Absolute pressure is the sum of the pressure due to the immediate fluid, like the liquid that was in that container, and the pressure due to the atmosphere above, if the container is open. The gauge pressure is a term for the pressure that's actually due to that immediate fluid. It's the difference between that absolute pressure, that equation we just looked at, and the pressure due to the atmosphere. So the equation I showed you be represented this way, that the pressure, which is the absolute pressure, is equal to the gauge pressure, that rho GH, the density times gravity times height, plus the pressure due to the atmosphere. And like I said, we're going to use 101,300 pascals. Now, another device that's used for measuring pressure is called a manometer. A manometer is a little different from a barometer in that we use it to measure gas pressures. Barometers we use to measure atmospheric pressure, which of course is a gas. But for a different gas, we would use a manometer. So we'd put gas in a chamber, and then we'd connect what's called a U-tube to it. Not the video service, but an actual U-shaped tube. And we filled that tube with a liquid, usually mercury. And so when we look at what's going on here in this manometer, right, we have gas pressure being exerted on this liquid mercury here, or this column of liquid, which is going to cause it to displace somewhat up the glass tube. Now, at the top surface here, so on this liquid, right, we have pressure due to the gas at the beginning, and we have pressure due to the atmosphere up at the top. But remember that pressure at the same height is the same. So our pressure at point 1 and point 2 are the same. And for point 2, the pressure we have is coming from the weight of that liquid, the rho GH, and the pressure of the atmosphere, which is 1 atmosphere. So to use a manometer, if I want to find the pressure of the gas, I just need to measure the height of the column and add atmospheric pressure to that. All right, so that's what we have for density and pressure in gas. See you in class.